Yeah, thank you, everyone. And we are very grateful to get the most notable paper award for our 2012 paper. And today I want to give you a quick overview of kind of a few highlights of what happened in the last 10 years in the world of our interpreter and VM research that is kind of going more or less under the name GraalVM. And of course, I'm just giving the talk here. I'm in no way the only person who did all that work. I'm speaking here for the whole GraalVM team, and both at Oracle and also outside of Oracle. So it kind of started 10 years ago with the first paper where we wrote up our ideas about AST interpreter node specialization. And the idea was pretty simple. It's like you want to write an AST interpreter, but you want to factor out your AST interpreter, write it in a nice way. So instead, for example, when you have a language where you have an add operation that works on numbers, like double and on strings, and you have a generic add, people might see some resemblance to JavaScript in this slide here. Then instead of writing one big interpreter method, you actually split these things out into 3 separate methods. You have the functionality for double addition, for string concatenation, and for the generic add. And even in this first paper, it was already clear, it's like, well, you only don't just want to write an interpreter, you also want to really have a compile system where you actually get very good peak performance. And writing an interpreter in that way is kind of the first step in getting good peak performance, because when you have an interpreter where all the types are specialized, then you can collect profiling feedback while the interpreter is running. So you specialize your AST interpreter, and then the kind of second step that builds on that, and if you carefully read the 2012 paper in the future work, it already kind of hints very strongly in that direction. Then you can actually do a partial evaluation of the interpreter. So you can take the interpreter and run your compiler over it, but in kind of inline all these type specialized execute methods, and get highly optimized machine code out of that. But of course, we are in the setting of a dynamic language, and all of these specializations are never set in stone. You always need to be able to go back and redo your decisions. And for that, the standard technique in virtual machines is deoptimization. So you can go back from the compiled code always to the interpreter and re-specialize in the interpreter, and then you can compile again. So you have this nice feedback loop where it's like you have a specialized interpreter, you do a partial evaluation for compilation, you might de-optimize back to the interpreter to change the specialization system. And that's actually a nice forward-looking paper that we then published in 2013 that kind of summarizes the whole truffle system pretty well, and it's still up to date. So it's like the whole idea that we wrote down actually worked out mostly as it is written up already in that paper. But of course, that was a very forward-looking paper without kind of an evaluation and with a lot of hand-waving. And then we spent a good number of years optimizing and implementing programming languages based on this system. And actually, it took us a couple of years until we really had kind of a good understanding of the real core primitives that you need to write an interpreter in such a system. So it's like, and in such a system, what I mean is like you write as an interpreter, language implementer, you write a simple interpreter, and that's your job as a language implementer. But then we, as the VM implementer, give you good compiled performance. So there are actually surprisingly few core primitives that you need to use in such an interpreter. You need to start partial evaluation somewhere. And once you have compiled code inside of one compiled method, you need to be able to trigger the optimization inside of a method and say, well, I went into a specialization that no longer holds. I need to trigger deoptimization, go back to the interpreter. But even more important is to have external invalidation of compiled code. So you can register assumptions, and you can say, in my big complete VM environment, I currently have the global knowledge that this and this assumption holds. And in your compiled code, you have zero overhead checking of this assumption, because when the assumption no longer holds, so when some external code calls invalidate on the assumption, then again, deoptimization is triggered and execution continues in the interpreter. So this zero overhead checking of assumption is very important, because zero overhead means you can check as many assumptions as you want in the interpreter, and you don't get any overhead in your compiled code. And you need to stop partial evaluation somewhere, so there are explicit boundaries, the same where there's an explicit starting point. So these four things are actually the core building blocks of when writing interpreters in the truffle system. But as always with core primitives, it's like they are nice as core primitives, but not the thing that you really want to use as a language implementer, because it's like assembly language. You don't want to write your system in assembly language. You want to write your system in a high-level language. That's why very early we came up with a kind of domain-specific language, kind of a fancy name for annotations in Java, and an annotation processor that actually does a lot for you, and you can really annotate just your interpreter method as this is a specialization in my interpreter, and then the domain-specific language generates all the code that uses assumption and that uses transfer to interpreter. So even though there are these core primitives that are used always under the hood, it's like when you write an interpreter, you actually you don't see them and you don't really use them directly. You mostly use this domain-specific language. Writing and implementing one language is fun, but going back even to our PLDI paper, I think it's kind of one of the best evaluated papers, because it's like in this one paper, we kind of have evaluation for 3 full programming languages, for JavaScript, for Ruby, and for R, already in this paper. And the nice thing is, once you are a kind of polyglot, you can nicely compose these languages. That was always kind of the main idea of why we want this system. It's like the world is polyglot. There are many programming languages, and they are here to stay. So there is no one has the idea to kind of say, well, I implement a new programming language that will kind of supersede all of them. And of course, you can ask Stack Overflow, well, why can't that be? It's like, well, not even worth discussing it. It's like, got closed, it's not constructive on Stack Overflow a long time ago, and I could not agree more to that. It's like, there is never going to be one language. But by having this system where as a language implementer, you don't have so much work to do because you get the compiler for free, we take a lot of effort out of language implementation. And by having many languages implemented in the same framework, you can compose languages. And that works very nicely on in the AST level or on the interpreter level, because it's like when you already have a nice interpreter where you have different operations. For example, here on JavaScript, where you have an assignment operation and you have a dot operation for the property lookup. Then to do polyglot lookup, you just need to have a special specialization state for the property lookup operator that does a polyglot interop read. And it's like now, instead of going to your JavaScript semantics to look up a property, you actually go to the polyglot interop system, and that says, well, the receiver of this property lookup actually happened to be, for example, a Python object. And then this AST specialization actually specializes in the property lookup of a Python read. That all works nicely, as I said, because your Python interpreter is written exactly the same way as the JavaScript interpreter, using the same specialization system. and so can seamlessly access and a Python object. The important thing here to note is like now you have JavaScript code that accesses a Python object, but there's no overhead at all. Because again, when there's this partial evaluation and the compilation, then the Python property lookup code is inlined into the JavaScript code as if it is a Python method. So there's no boxing of objects, no complicated meter object protocol where you need to wrap things. It's like there's no boxing, no performance overhead of when composing languages. And yeah, that's a very powerful feature of Truffle, and I think one of the best parts. I like it a lot in terms of the research results. Unfortunately, from a production point of view, it's like so far it's not used much because it's a chicken and egg problem. I would say it's like there are just not enough Polyglot applications out right now. So it's like it's difficult to convince real customers who have production application to compose languages. But I think on the long run, that is something that will change because the number of languages only gets more and more. So languages never go away. One of the things you can do here, for example, is when you have a Node.js application to start up a little web server, you can call from Node.js, from JavaScript to Java to do Java big integer arithmetic, because that's a class that Java just has. So you can look up the Java type big integer from JavaScript and compute 2 to the power of 100. But for example, you can call from JavaScript to R and run R code. And on the little more complicated example that maybe have the screenshot on the right side, it's like you have now a Node.js application where you embed a plot that's coming from R. So it's like R has a nice plotting library, JavaScript does not, but it doesn't matter because you can use your R plotting library from JavaScript. And that's where the real power of the different programming languages comes from. It's not the language itself. It's like, yes, you can have long discussions on the internet on which language has the better syntax, but that's kind of a useless discussion because the power of the languages comes from the ecosystem. And with R, for example, you have all the statistics, you have all the data visualization stuff, and you can use it now from JavaScript or from Ruby or from Python. What works for composing programming languages also works equally well on the tools side. It's like what Truffle provides you is kind of one tool interface that's language agnostic, and every language then can use the same tools that are implemented against this one tooling interface. That again works by having a language independent view on the EST. And for example, to write a debugger or a profiler, what you need is you need a view on your EST where you tell the debugging interface, well, that's a statement, that's an expression. So it's like that's where a new line starts so that you can do single line stepping. But when writing your interpreter, you don't need to do much. You just need to make sure that you correctly tag your nodes and say, well, in my language, this node is a statement, and in this in my language, this node is an expression. And as long as you do that, then all of the tools just work out of the box. And again, what really helps here is that you get all of these things like debugging, for example, with full performance. Because it's like as soon as you set the breakpoint somewhere, of course, you need to make sure that when the breakpoint is hit, you really go back and in the interpreter so that you can inspect all your values. But until you hit the breakpoint, you really want to execute the application at full speed, which works by inserting nodes into the AST that when the code is compiled using partial evaluation, just then compiles into machine code deoptimization and says, well, now the breakpoint is hit, go back into interpreter, and then in the interpreter you can inspect your stack frames, you can modify your local variables, you can do whatever you want, whatever debuggers usually do. But again, with this system, it's like with the separation of interpreters and the partial evaluation for compilation, you automatically get full speed debugging for all your programming languages. That can go very far. So for example, we have also worked on some sort of language independent IDE support. So it's like GraalVM supports the language server protocol, which is kind of one pretty standard way of connecting languages to IDEs. And again, you don't need to implement a LSP server for each of your programming languages. You only need to correctly tag everything in your language. You need to kind of implement a few interfaces, and then your language is ready for integration with all IDEs that support the language server protocol. There are lots of other papers that got published. I have, of course, not the time to kind of go into everything, but one thing I really like is kind of experiments that are around, for example, Polyglot live programming, where it's like, oh, you want to inspect values live in your IDE using, again, the LSP protocol. It's like just see what are the possible values of my local variables when you have a loop. And by doing that on the GraalVM and the truffle infrastructure, you automatically get that working for all languages. So it's like, it's not just working for one language like JavaScript. In that case, it's like, well, it's working for JavaScript and for Ruby in the same way, with the kind of the same infrastructure to insert, in that case, probes and assertions into your language, into your program. So yeah, in summary, we spent the last 10 years doing a lot of very interesting research. But the good thing of kind of being in a company research lab like Oracle Labs is like, well, you have a company behind who actually wants all of your stuff also in production. It's a good thing because it's like you have all the infrastructure and all the resources to go to production. But of course, it's also a lot of implementation work. But yeah, we were quite successful in getting all of that, like a couple of our languages into production. But first, I want to talk about a few more languages. So far, I only mentioned dynamic programming languages like JavaScript, Ruby, and Python. But of course, when you have a framework to implement dynamic programming languages, you can also implement static languages like C. And very early in our project, we actually implemented a C and an AST interpreter for C. Worked quite nicely, and we even got a paper out of that. It has advantages to run languages like C on a dynamic infrastructure, because you can also speculate and specialize your C code the same way you can actually speculate and specialize for JavaScript. So for example, you can speculatively inline function pointer calls based on your history that, oh, this function pointer call only had one coolie. But as soon as you start doing something in C, people come like, oh, well, but what about C++ or Fortran or all these other statically compiled languages? So it turned out really writing an AST interpreter for C is not really such a good idea, because what works for C, no one wants to implement for C++ because it's about 100 times the effort to do. But unfortunately, it's not really necessary to implement all of these languages separately, because there's LLVM. And so what we did instead is kind of we implemented a generic interpreter for LLVM bitcode. So a bytecode interpreter to interpret the bitcode directly. And with that in the GraalVM infrastructure, you can kind of also integrate all of these languages with dynamic languages like JavaScript or Ruby. It's especially important for languages like Ruby that have a very complicated C interface, where you have C extensions, and the C extensions are very tightly coupled to kind of the internals of Ruby, like how you access Ruby objects. And the only way to do that efficiently is actually to compile the C extension to LLVM bitcode and then interpret the LLVM bitcode and do Truffle language interop between Ruby and the C extension, so that you can compile things together and optimize things together. This LLVM bitcode interpreter was also kind of our first interpreter, where we really then went into bytecode interpreters. And I will talk a good bit more about bytecode interpreters later on. One thing that's also important for the ecosystem, and especially then when thinking about going to production use cases, is like, well, you need to embed all of your languages into as many different applications and use cases as possible. And for that, we have a pretty flexible interface where you can embed the Truffle languages either in Java code, or you can compile it down to native code to a shared library and load it from existing larger C applications. And the good thing again is, like, every language that's implemented in our framework can be automatically then embedded in all of these applications. So it's like you only need to write one embedding and you get all languages kind of for free. And that allowed us to actually deploy GraalVM in quite many settings already within Oracle in production. The by far most important thing for Oracle, of course, is the Oracle database. And with the MLE project, so the Oracle Database Multilingual Engine, you can run our Truffle programming languages inside of the Oracle database. So if you don't like PL SQL to do server-side scripting in the database, you can now use a JavaScript instead, thanks to Truffle. So that means it's like when you currently go to the Oracle Cloud and grab an Oracle database instance, then you can just use JavaScript and it works. That's fully deployed in production. One interesting case study here is like that uses the Oracle database is the Oracle Apex product, which is a low-code programming platform where you kind of click together your homepage and kind of do data-driven applications that way. And it's like not much change in Apex, other than now for the little code script snippets that you write, you can now select JavaScript as the programming language, and everything works the same way that it worked previously for PL SQL. So from Oracle's product point of view, that's kind of one of the big deployments of GraalVM. The second one I want to mention is like that all of that work runs in production in NetSuite, and when NetSuite customizes its platform using JavaScript, so it's like customers can provide little JavaScript scripts to customize the application. And when you use NetSuite, Oracle NetSuite these days, all of that runs on that platform. But of course, it's all open source, and you can use it without support from Oracle, or you can use it as a fully supported Oracle project standalone too. And there are lots of other external use cases. For example, the Dutch police is running R in production to integrate with their Scala applications on top of a GraalVM. A company called Adyen is kind of running C and C++ code safely integrated with Java code using Sulong, the LLVM bitcode interpreter, in the mode configured where it's like actually every C and C++ object access is kind of range checked and type checked, so you can run untrusted C code that's coming from untrusted customers without worrying about security problems. And companies like Enso even built kind of their whole company and their own languages on top of the language framework. So the Enso language is kind of a graphical data visualization language, and it's running on top of GraalVM and can interact with JavaScript, with Ruby, with Python, with all the other languages that exist in the system. Yeah, so it's very nice to see that the whole thing not only worked out on the research side, but also is used quite a good bit in production already. But of course, the interesting thing is always the research, and we are by far not done with research. There's a lot going on right now, both inside Oracle and outside. So we have a good number of university collaborations where we have PhD students working on all sorts of interesting things in GraalVM. One thing, for example, is in terms of languages. A very important language I haven't mentioned so far are regular expressions. Many people don't even realize them as a separate language, but of course they are a language, and every programming language kind of has an integration for regular expressions in a little different flavor. But what GraalVM provides is kind of a very language agnostic implementation of regular expressions that can be customized. So it's like every language that needs a regular expression engine and can just use and customize truffle regular expressions. And you automatically get very fast compiled regular expressions, because all the automatons that are created for regexes are kind of JIT compiled. Compiling a regular expression is kind of, and this automaton is kind of the same thing as compiling a bytecode interpreter. Speaking of interpreters and how you write interpreters, you might have noticed that in my talk title, actually, I did not say AST interpreters. I said a decade of interpreter research. And the kind of fight between AST interpreters and bytecode interpreters is still going on, and still going heavily, because of course AST interpreters have so many nice properties. It's so easy to write them. Every undergraduate hopefully can write one. Whereas for a bytecode interpreter, it's like you always have this high overheads. Like first you need to define a bytecode format, and then you have the bytecode interpreter loop that's ugly to write. You have a lot of boilerplate for that. But on the other hand, AST interpreters have one pretty significant downside, and that is the memory overhead and the startup overhead. So in the AST interpreter, you have all these separate AST nodes, and by writing that in Java, it's like every AST node is a separate object. There's not really much you can do about that. And that means that when you pass your language, you need to create all of these objects. You need to have them in the heap. You need to, by the specializations, you need to kind of replace one AST node with another one. There's a lot of memory overhead going on there. And bytecode interpreters don't have that problem. So with bytecode interpreters, you get very good startup, because as soon as you have the bytecodes, usually in the compact kind of byte array, or just raw data, where you just increment your bytecode index in the interpreter when going to the next instruction. The interesting thing what we learned over the last years is that, yeah, AST interpreters are so nice, but the inherent problems are something that we cannot really fix. So even after all these years, we didn't find a way to kind of reduce the memory overhead and the memory overhead of AST interpreters, and to kind of reduce the startup to increase the startup performance of AST interpreters. On the other hand, for the downsides of bytecode interpreter, that they are complex to write, we can fix that. And how can we fix that? Again, with our domain-specific language. So in our domain-specific language that we already have for all the specializations, you can actually write just another annotation and say, well, in my whole specialization system of integer types and double types that I have here. I say, well, actually, I have an equals operation, and I have kind of one annotation that says generate operations as the trigger of please give me a bytecode interpreter. And just with these few annotations, we can actually generate you a complete set of bytecodes and a complete bytecode interpreter, so that actually you think like you're writing a simple AST interpreter, but actually what you get is a bytecode interpreter under the hoods. And with that, we can actually give you all the benefits of bytecode interpreters without the downsides of bytecode interpreters. So that's all very heavily under development right now. So nothing of that is kind of released or used in production. But I think in terms of the research results, it's pretty important, I think, and will have a big impact. And our goal is so that eventually over the next years, we kind of convert all of our production language implementations to these systems so that we can eliminate the overheads of AST interpreters without kind of losing the benefits of AST interpreters. One other very important research area is security, because it's like secure execution of kind of user provided scripting code is very important. I already mentioned the use case from Oracle in the NetSuite product, where it's like, oh, customers upload JavaScript snippets to customize the application. But what with all the possible impacts of kind of random user code? What if you have malicious user code that kind of wants to exploit some vulnerabilities in your application, or just malicious code that wants to do a denial of service attack and just burn CPU cycles in an endless loop? So what we have under development to solve these problems is like a complete polyglot sandboxing system where you can run the truffle languages in their own isolated context. And you can create many of these isolated contexts within one process with very little overhead. And then the dynamic language execution is in this isolated context. And hopefully nothing can escape the sandbox. Luckily, also the hardware vendors like Intel helping us by implementing memory protection keys, for example. So by using memory protection keys, you can have an isolate that really is on the hardware level, kind of isolated and cannot even access memory from the hosting GraalVM from your trusted application code, because it would kind of end up in a segfault if you try to do that. So yeah, there's lots of very interesting research going on, not only on the language side, but also on the security side. Regarding GraalVM. So to summarize, what's the kind of a big picture of the whole GraalVM ecosystem? First of all, should be clear by now, everything that we write in terms of in the interpreters is written in Java. So you write your languages in Java and everything runs on a Java VM. The thing that glues everything together is the Graal compiler. I didn't have time today to kind of talk about it in detail, but it's one compiler that kind of makes all of these languages fast, and kind of everything is based on top of on the Graal compiler. And obviously, when you have a JIT compiler in a Java VM, you can run Java bytecode-based languages directly on this JIT compiler without the Polyglot truffle system. But when you go in our Polyglot truffle runtime, then you can implement interpreters for all your languages, and languages we really have and use in production: Node, JavaScript, Python, Ruby, and R. But then you have kind of this very powerful languages like LLVM bytecode, and with our Zulong interpreter, you can run all of these static languages like C and C++. One of the new kind of formats in this world is WebAssembly. And of course, we also have a WebAssembly interpreter on top of the Polyglot truffle runtime. So all the languages that compile to WebAssembly can also be integrated in the system. So it's like now you actually have two ways to run a C and C++ code in our truffle system. You can run it either on the LLVM-based system, or you can run it on the WebAssembly-based system. And then, of course, because for meter circularity reasons, we also implemented a Java bytecode interpreter on top of this Polyglot truffle runtime. So it's like when we want to really deeply integrate all of the Java bytecode-based languages, Scala, Groovy, Java, Kotlin, whatever, then you can actually use the Java bytecode interpreter in the truffle system, which is called Espresso. And you can run and integrate all your Java bytecode-based code also with the dynamic language code. Yeah, if you want to get involved with that project, as I said, Oracle is definitely heavily invested in that, and we have lots of full-time people working on that. But we are very open to research collaborations. We have lots of interns working on stuff. So it's like if you're a PhD student looking for an internship and in that area, please come talk to us. If you're a professor working in this area who wants to collaborate, please contact us. We are very open for all of that. With that, that is all that I have in my presentation, and I'm happy to answer any questions.
Thank you very much, Christian. One question already there.
One question I see in the chat. You talked about an
Let's start with a question on the room, Christian.
Sorry?
Sorry, I'll just ask my question. Hopefully this won't take too long. This is a really cool project. I've been following it for a long time, and it's pretty neat to see how it's evolved. But one of the things I'm curious about, particularly in relate to the polyglot concept, is it seems like you've done a lot to address the runtime problem. But one of the problems I've always had is how do you do like a distribution of a polyglot application? If you have an application that consists of all of these different moving parts, is there a good way to actually move that around to execute that on different platforms and so on and so forth? Have you done any work on that, or is that sort of too trivial of a problem in some sense?
It's definitely not a trivial problem, but it's like the good thing about every language is like the ecosystem, but the bad thing is, of course, that every language has its separate ecosystem. And so it's like, well, yeah, from JavaScript, you need to integrate with NPM, and for Python, you need to integrate with this with the Python package manager infrastructure. And no, we don't really have a good integration. The way to solve that, but there's nothing that we have implemented available for that right now, would probably be kind of an integration language to kind of have a package loading language as a separate truffle language that kind of interfaces and loads things from the different package managers. That would be for one way how this problem could be solved. So it's like so that you can kind of have a new language whose only purpose is to kind of fetch packages from different package managers and make them available for polyglot interaction. That would be one way to solve it.
Do we have another question? So while you think of questions, maybe one for the future. So we looked at the 10 years past. Where do you imagine the system to be in 10 years in the future? Or which kind of big problems do you hope to have solved?
Well, I hope in 10 years, GraalVM is the only VM that's around, and the whole world, all the languages run on top of GraalVM. Well, but okay. Maybe probably 10 years are not enough for that. But no, but in terms of research, it's like, yeah, as I said, it's like, I think we will invest a lot in kind of security research, because it's like from a company point of view, and that's very important. And we still have kind of a long way to go to really solve all the startup problems that we have in our systems. It's like we have shown that there's perfect peak performance. There are no problems from that point of view, but we need to kind of solve the startup problem. And we have a lot of that that I also did not talk about. So it's like there's, for example, a snapshotting system under development where you can kind of snapshot your application and kind of then avoid startup overhead by resuming from the snapshot. So it's like that's kind of one of the big areas of research for the next years.
Okay, thank you. Jeremy?
Thank you. Christian, thanks for a lovely talk. Very enjoyable. I've got 2 questions, if you don't mind. Number 1, in this diagram on the screen, you show many different languages, all supported. And my question is, are all the languages equal, or is Java the real language and the others just second-class citizens? And my second question, just quickly, you talk about isolation and somehow protecting parts of the system from other parts. Is that something you'd expose in an API to the application developer, or are the applications unaware of this isolation security? Thank you.
Yeah. Are all languages equal? Yes. There is nothing, no language is more important or better than any other. The fact that the implementation language of our interpreters is Java does not mean that Java is kind of implemented in any better way. And even in our kind of language agnostic framework, it's like there's nothing in the core interpreter primitives that we provide, in the core abstractions that we provide, that would be language specific. So it's like, no, all languages are equal, and that is by design, and I think a very important property. And the second question for isolation, yes, when you start kind of a context that is isolated, of course, you need to, when you start this context, specify what this context is allowed to do and how much memory it consumes, how much CPU resources it is allowed to consume, and kind of how the interaction with the host world is restricted or not restricted. So it's like there is an API to kind of configure that. And for example, you say, well, my isolated execution of this JavaScript snippet or this Polyglot snippet is not allowed to exceed kind of more than 100 level deep function calls to avoid kind of endless recursion and these kind of problems. Or you say it's like, oh, I give my execution a quota of at most 10 million instructions. And if you exceed more, then your execution is aborted. And that's one of the nice things. It's like, well, how do you abort execution? Again, via deoptimization. It's like you don't really need much counting and overhead in the optimized execution. It's like, oh, you constantly need to check, did I exceed my quota? Or, for example, or did I exceed my time budget in terms of 5-second execution time? It's like after 5 seconds, we can just say, well, we de-optimize everything back to the interpreter and throw an out of time exception. And then you go back and your application reports an out of time exception.
All right. Do we maybe have, I think you saw already the comment online, do we maybe have still an online question or in the room? While waiting for that, maybe one question also in the direction of security. You mentioned you're looking into Intel and hardware things. One of the interesting things in the UK these days is the Cherry architecture and ARM's Morello, where they have capability tag pointers. Is that something interesting to you guys?
Yes. Yeah. And it's like ARM, I think, even offers a little more than Intel, because Intel only has this 16 memory protection keys versus the protection system that's coming on ARM. It's like it's more flexible, which probably will allow kind of more separated isolates, and you can kind of use the tag pointers to enforce isolation of one particular execution context.
All right. It looks like that was the last question. So let's thank Christian again.